So as a reminder, the Crash Dummies lab was the one in which we set up the ramp and released the cart from 3 different release heights. And as we were releasing that, we measured the velocity of the cart again, and then also measured how far a crash dummy was thrown following an impact with a heavy book. So this kind of takes the velocity lab and then goes one step further with the momentum lab. And from here, we've gone another step further. So we're not just crashing the cart into the book anymore, but we're crashing the cart into the book and measuring how far that dummy flies across. So now it's not just a transfer of force and a transfer of momentum, but we're also measuring in a kind of a roundabout way the inertia at play here. That dummy, the little guy sitting on top of the cart, continues to move after the cart stops moving. That's a demonstration of Newton's first and second and third laws there, the action force and reaction force, and the dummy flying through the air after the rest of the equation kind of stops moving. So that's just kind of a quick rundown. So once again, your lab should be set up. Here's the Word document. You should have your name. You should have Crash Dummies Lab up at the top. Then you need your data table. And your data table should have all trials. And from those trials, you should have you should have velocity. You should have the distance the dummy is thrown. Then you're going to have 2 graphs. And those 2 graphs will represent the 2 things, 1, 2, that we measured. And will include just the averages. From there, we will then have your discussion paragraphs, right? Or paragraph. Remember that when we title this thing, it should be your last name, underscore, Crash Dummies 1 or 2, depending on if it's the first or the second, the final draft. So to get into the discussion section here, well, quickly let's talk about the graph title. The easiest and probably best way of creating a graph title is to say the effect of whatever the independent variable is on the dependent variable, and then adding some context. So, for an example, the effect of snow days, independent variable, on student happiness during a cold winter. See, here's your independent variable, here's your dependent variable, and there's the context, right? You don't actually want to write these 3 things in your lab titles. Those are just to call out what those different variables are, which is what I wrote right here. So, as usual, you cannot take these 2 word for word, but this one you can. So when we're writing our discussion paragraph, the first thing that we need to do is an intro. And within that intro, we're going to have a general purpose statement, and then we're going to have a setup statement. So this one goes over setup. It's on you to come up with a general purpose statement. We've done it with both the velocity lab and the momentum lab. Remember here that the purpose was for students to measure the impact of, or the effect of, release point on not just the velocity of the car, but also on the distance the dummy was thrown. I kind of just gave you the answer. Then, here's an example of a setup sentence. Again, don't use that word for word, but you can write something pretty close. Then we want to talk about results. The first thing we want to do is a general statement. Did the numbers go up, or did the numbers go down? Then, we want to talk about specific numbers from your trials. You can use this sentence starter. You probably should use that sentence starter. It's a very concise, easy way of saying everything in one sentence. Then comes the fun part. We've got the discussion section. Within that discussion section, we've got a couple tasks. The first thing we need to do is talk about why those results happened. So within that why, we're going to need to talk about the series, the force of impact, and inertia. Then we're going to talk about errors. Then we're going to talk about future experimentation. So within this discussion section, the first thing we talk about is the series. I list out for you kind of the series right here. By changing the release point, we're changing the distance, which allows the cart to travel for a longer amount of time, which means that it can accelerate due to gravity for longer, which increases its velocity. Just like in the momentum lab, this also increases the momentum, because as the cart is traveling faster, mathematically that increases its momentum. Therefore, when it hits the book at the bottom of the ramp, it's going to transfer the force from the cart into the book. That book will move, the cart will stop moving. This is where we go into that force of impact conversation that we had about momentum. More on that in a moment. Then we talk about, we need to answer why the dummy moves further. Right? Why does the dummy move further? We're going to talk about that in a moment as well. But that's kind of the series, as well as pieces of the force of impact and inertia to talk about. This little notes here is going to need to be expanded somewhere into the range of 3 to 4 sentences. Right? That's a tough thing to do. That's a tough topic to talk about. Increasingly, when we went from velocity to momentum to now crash dummies, it's gotten increasingly complicated and a little bit more challenging, which is why they're done in this order. We'll come back to that in a little bit more. Then, when we're talking about error, remember that we do not want to talk about human error. Right? We don't want to talk about me messing something up or you messing something up. We want to talk about what is different group to group. Did different groups have different things? I give you a couple examples. Finally, with your future experimentation, once again, you want to keep the track the same, the cart the same, and you're still measuring velocity and the distance that the dummy is thrown, but you're changing the independent variable. We've already tested the release points. So what else could you test, right? And try to think of something other than changing the angle of the ramp or the height of the ramp, because we've discussed that a lot. What other aspects could we change, right? What other things that we controlled in this lab could we change? So I would ask that you keep the angle of the ramp the same, and we're still measuring velocity and still measuring how far the dummy moved. But what else about the lab could we change, right? I'm asking you to go a little bit further with this one. So to go back up to that why, with the series, the force of impact, and inertia. I've drawn out a little bit more detail here. I give you another example, right? 2 examples of error right there. But when we're talking about this discussion section, here's your series, which brings you to force of impact, right? Velocity, momentum, transfers the force, force of impact. If you're confused about the force of impact, the best place to go is the momentum video, because the momentum lab video has tons of details. I talk about it for 5 or 7 minutes in there. I'll go over it really quickly. Because the velocity of the cart is higher when it's released from a higher release point, but the deceleration time, is instant. That means that the rate of acceleration, or negative acceleration, deceleration, is greater. So as it's released from a higher release point, the velocity will be higher. As the velocity is higher and the deceleration time is instantaneous, that means that the rate of deceleration, because that initial velocity is now greater, is going to be even higher. So if acceleration has gone up, therefore your force of impact has gone up. This we all proved in the momentum lab, right? Now what gets tricky is answering, why does the dummy move further than the book did, or than the notebook from the momentum lab? Right? When we hit that momentum in the momentum lab and we hit that book at the bottom of the track, it moved 1 centimeter. It moved 2, maybe 3 centimeters. The dummy flew 1 meter, right? So why is the dummy flying 1 meter, whereas the book moves 1 centimeter, right? So the book moves, let's say, 2 centimeters. The dummy moves 1 meter, right? 50 times as far as the book. So why is that the case? Now, if you said because the book is a lot heavier than the dummy, you are 100% correct. But that can't be our final answer. We can't just say, well, the book moves the book doesn't move as far because it's so much heavier, whereas the dummy's really light. You're correct, but we need to explain why. And the reason why gets us into inertia. When we're talking about inertia, we know that heavier objects with more mass, are more resistant to changes in their state of motion. So that really heavy book is really hard to get moving, which is why it only moves 2 centimeters. But that really light dummy that's already traveling down the track really fast is going to continue moving really fast and is going to fly really quickly because it has all of that inertia from all of its motion. Also, is there any force of impact directly tied to the dummy? When we think about the cart slamming into that book, the cart stops eventually. Yes, it bounces back, but eventually it stops moving. The book moves a little bit, but it stops moving pretty quickly as well. What we see moving for a lot longer and a lot further is that dummy, and that's because it's not connected. Right? So that then brings us to this question. What if the book weighed less? What if it had less mass? If the book was less massive, and therefore it contained less inertia, then it's going to move a little bit further. If instead of 2 centimeters, it moves 10 centimeters, what happens to how far the dummy moves? It's a really hard question. So now we're not just saying, okay, so the cart slams into the book moves a little bit, but the dummy, not being connected, still has inertia and continues to move really far because it's so light. Now we're saying, well, it also matters how heavy that book is, which is why that's one of the errors. So if that book weighs less and therefore is going to move further, that means that action force, reaction force, Newton's third law, collision, happens a little bit slower. And by that I mean when that book slides back 10 centimeters instead of 2 centimeters, that instantaneous transfer of force takes a couple instants longer because it's essentially that lighter book is cushioning against the impact of the cart. So as it's cushioning against the cart, that adds time, which means that if that action force, reaction force is happening slower, that means that some of that action force is wasted on friction. Friction from the book sliding across the ground as it's moving 10 centimeters instead of 2 centimeters. Now, just like in the momentum lab where we hit that really hard part of explaining the force of impact and the transfer of force, this is now the really hard part of the crash dummies, explaining this piece here. That not only is it just inertia, and not only is it just that the dummy's not connected, but because the dummy's not connected, and because the book is relatively heavy, the dummy goes flying. If the book was a little bit lighter, maybe the dummy wouldn't go flying quite as far. That might be an interesting future experimentation. I'm going to draw a couple diagrams to help with this, but this is the tough part. So remember, if you've got your intro with the general purpose, the setup, the results that go general and specific, and you go through in your discussion section, you talk about why, using the series, force of impact, inertia, and you start to get into the action force, reaction force stuff, you can still do quite well in the lab. Don't forget that with errors, we're not talking about human, and future, you're changing a different independent variable than the angle of the ramp. Let's find something different to test than just the angle of the ramp. So I'll draw some diagrams. So here's a little diagram. Hopefully this helps a bit. So as the crash dummy, this guy, is going down the track on the cart and is gaining speed because of gravity and the longer distance, more time, etc., etc., it has a collision right here with this book. This dummy not being connected, instead of it being part of this collision, keeps flying off. Whoa! But as this cart here hits this block, this book right here, this book is going to move a little bit. If it's a heavy book, it only moves something like 2 centimeters. And the reason that it only moves 2 centimeters is because this cart only has so much force. It reached some velocity, and upon impact, it decelerates close to instantaneously, which tells us its deceleration, which we can then use to multiply against the mass to find the force. It will apply that force to this book, which will then move the book a certain distance. It doesn't move it further because there's friction with the rug. Now, if this book suddenly became lighter, right, if we erased half of it, showing that it is less massive, right, it's smaller, and therefore probably has less mass to it as well, it's no longer going to just move 2 centimeters, it's now going to move 10 centimeters. As it drags for 10 centimeters, there's going to be 5 times more opportunity for that book to encounter friction along the carpet. So as this cart is now slamming into this book, this cart is also going to travel a little bit further as it continues to push this lighter book. So as the cart pushes a lighter book, not only does the book travel further, but the cart travels further. And as that happens, this release of our crash dummy is not going to be as instantaneous. Yes, he is still not connected to the cart, but however, since that collision down here is not so fast and quite so instantaneous, but happens over a greater distance and therefore a greater time, that transfer of force, that force of impact, isn't going to be as great and isn't going to send this guy quite so far. An example that comes out of the book is, and you all know how great I am at drawing cars, so if you're driving a car, here's me in my car, yep, that's what it looks like, and I have 2 choices. I can drive straight into a brick wall, right? Here's my brick wall. If I do that, bang, boom, massive explosion, casualties, I'm probably dead, right? If, instead, I have the option of driving into, and here's a straw, a bale or a big thing of straw here, I can drive into a wall that has a huge mountain of straw in front of it. Which one do I want to do? Drive straight into the wall or drive into the bale of hay which is in front of the wall? Well, I would obviously not pick option A, I would pick option B. The reason for that is not that the bale of hay is necessarily going to completely stop me, but as I slam into this, I need to compress all of this hay before making impact with the wall. The fact that this bale of hay increases the time of impact. There's more time until I hit the wall. Because there's more time until I hit the wall, that means that my rate of deceleration will be slower. Remember before, we were assuming that our rate of deceleration was bigger, not because the time changed, but because the initial velocity was higher when you're released from a higher point. Now we're adding time. So if it's v2 minus v1 over t, and before we were talking about when released from a higher release point, the velocity getting bigger, right? We slowed down to 0, but instead of only moving 2 meters per second, we were moving 10 meters per second. That would increase your acceleration. But now what we're talking about is that with a lighter book, this time number gets bigger. If something in the denominator gets bigger, the overall value of this would be smaller. So the whole point is that you want to add time. This is why we have airbags in cars. Because if we didn't have airbags and we didn't have seat belts, when you slammed on the brakes or you got into a car accident, your whole body would move forward instantaneously and slam into the steering wheel, and you'd get really hurt. Instead, you have a seat belt that holds you in place against the car seat, and also you've got airbags that pop out of that steering wheel and hit you in the face. But as you are then slamming into that airbag, that literally bag filled with air, that is increasing the time that it takes for you to come to a complete stop, and hopefully you hit the bag full of air rather than hitting that hard circular wheel that is in front of you, because it's much nicer to be stopped by a bag of air that takes you longer to decelerate than it is to slam into a steering wheel. So the reason that you have airbags is the same reason that you would want to drive into the bale of hay rather than driving straight into the wall, which is the same reason that a book that is less massive than a book that is more massive will send the little guy flying a shorter distance. So a less massive book means that there's more time in that deceleration with the cart, which means that the little guy does not fly as far. Now this is all really hard and confusing. And remember, all that we've been talking about for the last 10 minutes has to do with this last 2 pieces right here. So if you've done this, you've done this, you've done this, you've done this, you've done that, you've talked a little bit about inertia and the guy not being connected, but you don't really understand what's going on over here, that's okay. Don't worry about it.